Hello, this is Jack Jackson. In this video, we're going to be looking at an application of integration where we compute volumes of solids by slicing where they have elementary shaped slices. So one of the most obvious extensions of the idea of using integrals to find areas of two-dimensional regions is to also use them to find volumes of three-dimensional regions. We will pick up on this topic further in Calculus 3 when we study calculus of multivariable functions. However, it is now time to compute some volumes of some very specific classes of three-dimensional solids. So let's recall that the basic process of finding an area was as follows. Break the area up into little slices, which we approximated with the area of a known figure, a rectangle. Sum the areas of these rectangular slices, producing a Riemann sum. Take the limit as the number of slices goes to infinity and their widths to go to 0. That produces an integral which we find. Over the next three sections, we will apply the same basic process to finding volumes. Break up the volume into little slices, which we approximate with the volume of a known figure, a triangular prism, a square prism, a circular cylinder, cylindrical shell, something like that, etc. Sum the volumes of these slices, producing a Riemann sum. Take the limit as the number of slices goes to infinity and their thickness goes to 0. And of course, let me add that fourth step, solve the resulting definite integral to find the area or volume that we're looking for. And of course, we can use the fundamental theorem of calculus to do that exactly. Or once we set up the definite integral, we can use a calculator approximation techniques to get an approximate value for that area or integral if that's all we need. So in this section, we will find the volumes of three-dimensional solids that can be sliced into parallel slices so that each slice has a cross-sectional area of a geometrically similar figure. Okay, so all the cross sections are similar in area to each other. For example, the slices may all be squares, or they might all be equilateral triangles, or they might be all, say, similar right triangles, or some other kind of situation where they're all similar shapes. So we're going to look at several examples. In this video, I'm just going to introduce one example. And the example I'm going to look at is going to turn out to be a solid with square cross sections. Now, the illustrations in this section will use the following GeoGebra activity created by Tim Brzezinski. In the activity, the user enters formulas for lower and upper bounds of a region in the XY plane. Left and right limits, a and b respectively, are also entered, and the graphs of these two functions are displayed on a horizontal XY plane. The area enclosed in the XY plane there is the flat base of the solid. The solid then rises above this so that cross sections perpendicular to the XY plane are always squares. Using the mouse, one can zoom in and out and rotate the figure to see it from different perspectives. And here's a link to the activity. I have it already pulled up. I'll look at it here in a minute. And so let's look at this an example. And by the way, while I'm saying this, Mr. Brzezinski here has also made similar activities for all different kinds of cross sections, not just squares. I think he's got one for rectangles and triangles, different kinds of triangles, and several others. And we'll look at some of those in these notes as well. But right now, let's look at this example. So here's the example that we want to do. So the problem here is in the blue text. Find the volume of a solid with a base in the xy plane bounded by y equals sine of x plus 3, y equals 0.2x minus 5. So that's a sine wave and a linear function on the top and bottom respectively. X equals 0 and x equals 6 for the horizontal sides. And then the cross sections are parallel to the y-axis and perpendicular to the xy plane. In other words, slices for a constant x. And those slices are squares. Okay, so I'm going to first just use basic GeoGebra to graph this. And so I just entered f of x equals sine of x plus 3. The way that I did this in GeoGebra to get it to stop from here, I said, I think I just typed in the algebra view, I typed in function, sine of x plus 3, comma, 0, comma, 6, so it'll only graph that part of it. And then similarly, I typed in g function 0.2x minus 5 comma 0 comma 3 0 comma 6 to get the bottom here, and then I also then typed in integral between f and g from 0 to 6 to get the shaded base there, and it calculated the area of that base, which is 44.4 repeating, looks like, or at least 44.44 to 2 decimal places anyway. It may not be a repeating decimal. And so we get a look at that base there. Now, then what we do is we take a representative strip, which might be right here. Okay. So here this is in GeoGebra. Where'd it go? Okay. And so I can move this point A and show you the little representative strip. So that's a constant x value gives me a strip that looks like that. Now, no matter where it is, the top is sine of x plus 3. The bottom is 0.2x minus 5. So if I take the top curve minus the bottom curve, I get the length of that strip, or the height of that strip. Okay, so we get the length of that strip. Its thickness is going to be some delta x. And then we're going to go straight above this, coming out of the screen toward you, is the rest of the, so that this makes a square for this strip. And of course here we get a bigger square here, and a smaller square here, and in between, some squares in between size here. And so the squares are going to get bigger and smaller. So the height of this thing is going to be the same as however long this strip is. So at some place it's relatively short here, and then it's bigger here, and biggest right in here, and then somewhere in here, probably somewhere in here it's biggest, and then wherever the graph of this is parallel to this line down here, where the tangent line up at the top is parallel to this one, will be where it's the biggest, and so forth. But anyway, the point is no matter where you are here, the cross sections are squares. And so you get a volume of a little prism which has width of delta x and a base and height of, sine of x plus 3 minus parentheses 0.2x minus 5. If we distribute the minus, that's C3, C minus and negative 5 is plus 5. And so we get 8 there. Okay, so again, this is the base of the figure that we're looking at. The top is given by this curve, the sine wave, and the bottom is given by this linear piece here, for a height given by the difference in those two, which turns out to be sine of x minus 0.2x plus 8, and for some x value within a strip, and then the width is delta x. So the full slice is approximated with a square prism. This sine of x minus 0.2x plus 8 is both the base and the height, and then the thickness is delta x. So the area of the cross section of sine of x minus 0.2x plus 8, and then square it, is the area of the cross section. Remember, again, that's coming out of the screen towards you for the square, and the cross sectional, that should say volume now, is approximately that times the thickness delta x. So we add up all those from k equals 1 to n, and we have a Riemann sum approximation for the volume we're looking for. Take the limit then as n goes to infinity, and of course delta x goes to 0, and we have an integral representing the volume. So in this integral, here's the integral right here, the delta x becomes dx. So you want to think of basically that width of that little strip as being dx. It's an infinitesimal width. It's what happens. It's really delta x, but we're going to take the limit as that goes to 0. And then we have our function here, and we're integrating from 0 to 6, and that integral is the exact value of the volume we're looking for. Now here's what this solid's going to look like. Remember, this is the base right here. And that base is down here in the XY plane. It's the bottom of this thing that's kind of in the green shape down at the bottom. And then above that, we come up as a square. So here's maybe our strip that we were just showing, or one similar. And then we bring that up, it makes a square. And the height of that square is going to vary, so the top has a curvy shape, pretty similar to the original sine wave there. Okay, and this is what the app looks like when you can substitute these things in. So here we have the app open, and you can see the shape here. I could change A to some other value by sliding that, or by just typing in a number there. Our value was 0. And again, you can change B the same way. Our number was 6, so we're going to leave it at that. You can change these formulas to different shapes. And this thing right here is changing where the strip is. But notice, no matter where that strip is, the shape of that is actually a square. Now we're looking at it from the side there, but it is a square. Now I can actually get this and move it around. If you look at it dead on this way, you can see that those shapes are all actually squares. They're getting smaller and larger size depending on how wide it is, which is the same as the height, because they're squares. If we turn it up this way, it's turned around, but that's the base that we were looking at a while ago. Well, let's see, it looked kind of like that in our standard orientation. But if I can get it, let's see if I can get it back around. But anyway, there we go. That's what the shape looks like from sort of various viewpoints. Okay, so you can kind of get an idea of what that looks like. Okay, so we got an integral. We got it. We've got it. So the exact value of this volume is that value of that integral. Well, let's go ahead and evaluate that, compute that integral. Let's go ahead and use the fundamental theorem of calculus to get a exact value there. This function is continuous over that interval, so we can do the fundamental theorem of calculus. And in the process, we're going to use a power-reducing trigonometric identity at one point, and we're going to use integration by parts at one point. Now, the very first step is going to be expanding this square out and squaring and getting this longer term here. And the details of that are worked out with this part right here, using long multiplication, or the distributive property. In other words, sine of x minus 0.2x plus 8 times itself is this. 8 times 8 is 64. 8 times the negative 0.2x is negative 1.6x. And then we got an 8 times sine x here. Negative 0.2x times 8 is negative 1.6x, which I lined up under the x's to line up like terms. Multiply two negatives here makes it positive. 0.02 times 0.02 is 0.04. 0.2 times 0.2 is 0.04. There we go. And then the x times x is x squared. And then we have negative 0.2x times the sine x out here. Then we take the sine x times 8 is 8 sine x, which I lined up under the other sine x term there. Multiply these together, we get an x sine x term here with, again, the coefficient is negative 0.2. And sine x times sine x is sine squared of x. Now I've lined up the two places where we had like terms, 3 places where we had like terms, and I can add those up. So we get sine squared here of x. Add these up, we get negative 0.4x sine x. Here we get 16 sine x. Here we get 0.4x squared, negative 3.2x, and 64 all added together. And so that was our first step to replace that square, 3 terms squared into these 6 terms here. Now, of course, one thing we have is we have this integral. The antiderivative of the sum is the sum of the antiderivatives. So I'm going to break this into parts. The harder ones I'm actually going to put toward the end. So I'm going to take this negative 4x sine x, put that integral at the end. That's the part we're going to have to use by integration by parts on. And the integral of the sine x, sine square of x, I'm going to put here. That's just sine. There's no 16 there. Hopefully luckily the rest of it's correct. So that's just sine square of x there. And then this part here, let's see where I've got those two. This is going to be 16 sine x, which is 16 times the integral of sine x. And then this is just a polynomial, so I'm going to leave that there. And I'm just going to write it all as indefinite integrals, and then at the end, I'm going to evaluate from 0 to 6 at the whole end. Okay? So let's see what we can do with that. I'm going to leave this part alone for a minute. Sine square of x is 1/2 1 minus cosine of 2x. So I'm going to use that power reducing identity to integrate that even power of sine there. And the last part, I'm going to use integration by parts. So let me look at the integration by parts. So here I want to, if I can see it all on the same screen, I've got negative 0.4x sine of x. If I let the u be the negative 0.4x and the dv be sine of x dx, then what I have is the integral of u dv. Well, I do the derivative of the u to get negative 0.4 dx. I do the antiderivative of the dv to get v, which is negative cosine of x. So the derivative of negative cosine x would be sine x. So that works out. And so when you have the integral of u dv, the integral of multiplying the first two here, you get the product across this way, uv, which is going to be positive 0.4x cosine x, 0.4 x cosine x. Let me fix that. Okay. No, not there. Yeah, there. It's right. It's right. It's right. Never mind. 0.4x cosine x right there. Minus the integral of v du. So let's see. Minus comes from the integration by parts. And then I'm going to, that's here, minus here. Yes, this does have an x there. That's the one that was missing. But I do have it correct in the next one down. Okay, there we go. Back to here. So we're going to minus the integral of v du. So with the minus from integration by parts, these two minuses cancel. So it's 0.4 cosine x dx. Okay, but then the minus is from parts. And we're going to integrate from not 0 to 5, but 0 to 6. So many little details here. It's easy to make a mistake, so you have to be careful. Okay, and then let's see what we can do now. So let's go back here. So I sort of did the hardest part first of the integration by parts at the end. So at the first, the integral of sine x is antiderivative is minus cosine of x. So again, take a derivative here, you get 16 and then the sine x. Here, the power goes up to 3, divided by 3. So 0.04 divided by 3 goes there, and that x to the third. This goes to x squared and divided by 2, so that becomes negative 1.6. This picks up an x, so 64x. Here we have the integral of 1/2 dx, which is going to be 1/2 x. And here we have the integral negative 1/2, the integral of cosine of 2x. Well, the integral of cosine of 2x is 1/2 of the sine of 2x, so the half and the half makes a fourth. That minus makes it a minus, so let's just double check this. If you do the derivative here, the sine of 2x is cosine of 2x times negative, so you get negative 1/4 cosine of 2x times the derivative of 2x is 2, makes it negative 1/2 cosine of 2x, and there's the 1/2 negative, and then cosine of 2x, so that's correct. Okay, and then this one here, we've already did this integration by parts, this part of it here. So there's the uv, and the integral of v du is this integral. Well, that's just going to be negative 0.4 and then sine of x. Derivative of sine x is cosine x, so that works out. And eventually now we got to evaluate from 0 to 6. I'm going to clean it up just a little bit. I want an exact value, so I'd rather have just fractions here. So I'm going to change everything to fractions that I can. 0.04 divided by 3, that's 4 over 100, and then divided by 3, 4 over 100 reduces to 1/25, and divided by 3, that's 1/75. So this is 16 tenths. 16 over 10 reduces to 8 over 5. That's negative. And I've got to get common terms here and get this together as one x term. So 64 is 128 over 2 plus 1 more is, let's see, positive, yeah, 120. Let me check this out. Hang on a second. Okay, so let's see where we were here. Yeah, that was 129 over 2. So that was 64 is 128 plus 1 more is 129 over 2. Okay, and I'm going to write sine of 2x is 2 sine x cosine x. The 2 times the 1/4 is 1/2. It is still negative. And 0.4 is 2/5. 4/10 reduces to 2/5. And again, 4/10 reduces to 2/5 here. All right, so in that form, I'm going to go ahead and evaluate from 0 to 6. So I take this just like it is and plug in 6 for all the x's here, here. X there, 6. Both x's here, 6. That x is a 6. There's 1, there's 1, there's 1. Now take the whole thing and plug in zeros everywhere. 0 here, 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 0, and there, zeros. Okay. Now the good news is looking at the back side of the thing, a lot of it is 0. Sine of 0 is 0. 0 times something is 0 here. Sine of 0 is 0, so that term's 0. 0 here, 0 here, 0 here. So I get 1, 2, 3, 4, 5, 6 of the terms are 0 on the last part. Cosine of 0 is 1, so these two negatives make plus 16 there. All right, well, I guess I'm working from the back, so let's just keep going. So this is nothing to do here. Negative 2/5 sine of 6. Nothing. Well, I can do this. 6 times 2 is 12, so that's 12/5 cosine of 6. Nothing I can do with that term to simplify it. 6 divided by 2 is 3 times 129 is 387. 6 squared is 36 times 8 is 288, so it's negative 288 over 5 for that term. One of the 3's here, I can cancel that down to a 25. And then I've got 6 squared is 36. And then the other 2 makes that a 72. And nothing I can do with the first term. So we got the negative 16 cosine, oops. I'm sorry, it's right. I've got a negative, let's see, I've got a negative 16 cosine of 6, and I got a 12/5 cosine of 6. Negative 16, let's see, make that into fifths, multiply top and bottom by 5. That's negative 80 fifths. Hang on a second. Okay, so where were we? Negative 16 here plus 12/5. So that's negative 16 times 5 is negative 80. Negative 80 plus 12 is negative 68. So that's negative 68/5 cosine of 6. That's correct. We've got our negative 1/2 sine 6 cosine 6 here. And then we've got our negative 2/5 sine 6 here. And then the rest of this is constant, so we can add up. 72 25ths minus 288 fifths plus 387 plus 16. Just do that on your calculator and change it to a fraction form. If you did it by hand, you're going to have to get a common denominator of 25. Get all those as a common denominator fractions and add the numerators. And if you do that, I'll leave the details to you. That's 8,707 over 25 for an exact value of negative 68/5 cosine of 6 minus 1/2 sine of 6 cosine of 6 minus 2/5 sine of 6 plus 8,707 over 25, or approximate value of 335 0.467595353. Okay, now we can check this with a graphing calculator. So here I used a TI Nspire CAS, which will find the exact answer. We can also check it with the TI-84 by checking that the approximations work out the same. So basically type what's in the box here in your calculator, being sure you're in radian mode, of course, and you'll get this decimal approximation. And then once this integral is set up, type that integral in as a approximate integral in your calculator, and you should get the same decimal value. We can get the exact value from a TI Nspire CAS by doing this, just integrating from 0 to 6. Here's the original functions that we're integrating to find the volume. And then it turns out to be this. That's kind of messy, so I told it to expand that previous answer, and that's exactly what we have. I think the first two terms are in the opposite order from what we have, but you can check that against what we have right there in the box. There's the negative 68 cosine 6, minus 1/2 right here, minus 1/2 cosine 6 sine 6, that's it. And then minus 2/5 sine of 6, that's here. And there's the fraction of this, the constant term, which is right there. And then, of course, I can have it do an approximation, and I get the same thing there. Okay, well, that integral was kind of long. It involved some pretty basic integration, but then also some expanding out here. So we had a lot of terms to deal with. Part of it was a polynomial, just a sine term. That was pretty easy. But this part here, we had to use a power reducing identity through there. Here we had to use a integration by parts on the last piece. And then there was a lot of evaluating to go on, a lot of fraction arithmetic to deal with as well. Luckily, a lot of the terms were zero, so it made some of it easier. But we were able to come up with an exact value of that volume that we were looking for. So the volume of that thing is exactly what's given in that box right there, or about 335.5 cubic units. And so that is an example of how we can do this type of problem. And the nice thing is this thing here will illustrate other problems of this same type where the cross sections are squares by just changing the top and bottom formulas that are given here for our strip. The basic idea of the whole thing, though, just remember, slice it up, describe what the volume of that slice is, add those up, take a limit, and that defines an integral for us. And then we can either evaluate that integral approximately if all we need is a decimal version using a calculator, or we can use the fundamental theorem of calculus to find an exact value using our techniques of integration that we've learned in our previous unit. All right, we'll do some more examples in the next few videos.